Here's the question this video is actually about. Can the James Webb Space Telescope, a telescope that has never once directly seen a moon outside our solar system, detect an active volcano erupting on one anyway, from 20 light years away, without ever resolving the moon itself? A team of researchers just told the scientific community the answer might be yes, not "we found one, nobody has." But a paper accepted for publication in the Astronomical Journal lays out a method for spotting these worlds, nicknamed Exo-Ios, by watching what their volcanoes do to their planet's aurora, not by looking for the moon at all. And the odds they calculated, using real JWST data on a real target 20 light years out, are good enough that this stops sounding like speculation fast. Stay with me, because the trick they're using isn't new. It's borrowed directly from something that's been happening in our own solar system for billions of years, right under Jupiter's nose. And by the end of this video, you'll understand exactly how a telescope can see a volcano it can never actually see. If you're new here, this channel breaks down real space science stories in detail. No filler, no science fiction, just what the research says and why it matters. Subscribe button's right there, cost nothing. Let's go back to the beginning. To understand how you'd hunt for a volcano you can't see, you first have to understand the one moon in our own solar system that makes this whole idea possible. Io. Io is one of Jupiter's 4 largest moons, roughly the size of Earth's own moon, and by every reasonable expectation, it should be a dead, frozen rock. It's small, it's far from the sun, there's no reason for it to have a molten interior at all, and yet Io is the single most volcanically active body anywhere in the solar system, more active than Earth, more active than Venus, more active than anything we've ever pointed an instrument at. Hundreds of active volcanoes, molten rock erupting hard enough to escape the moon's gravity entirely and shoot straight into space. Small bodies cool off, that's the rule. Io shouldn't have any internal heat left at all, let alone enough to stay geologically alive. It breaks the rule because of Jupiter. Io doesn't orbit Jupiter in a perfect circle. Its orbit is slightly stretched, tugged out of shape by the gravity of neighboring moons, and because Jupiter is so enormous, that small deviation is enough. As Io swings closer and farther from Jupiter on each pass, Jupiter's gravity squeezes and releases it every single orbit. That flexing generates friction. Friction generates heat. Heat that has nowhere to go except out, through hundreds of volcanic vents, forever. Scientists call it tidal heating, and Io is the textbook case of what happens when a small world gets caught in a gravitational chokehold it can never escape. On its own, that's a strange fact about one moon. It stops being just that in about 30 seconds. Everyone who's seen a photo of Jupiter has seen its aurorae, bright curtains of light near the poles, not unlike the northern lights on Earth. Most people assume that light comes from the same place Earth's does, charged particles blowing in from the sun. Some of it does. But a significant piece of Jupiter's aurorae isn't sourced from the sun at all. It's sourced from Io. Those volcanoes aren't just erupting lava. They're erupting gas, sulfur and oxygen, blasted off the moon's surface and out into space. Jupiter has one of the most powerful magnetic fields of any planet in the solar system, so that gas doesn't just drift away. It gets captured, dragged along invisible magnetic field lines all the way from a moon, millions of kilometers out, down into Jupiter's upper atmosphere, where it collides with other particles and lights up as aurora. Read that again. A volcano on a moon is partially responsible for light shows you can see from Earth-based telescopes. Nobody designed that. It's just physics. A volcanically overactive moon sitting inside a planet-sized magnet, doing exactly what that combination would do. And that's the exact chain a team of researchers realized might be detectable somewhere else entirely. Moon erupts, gas escapes, magnetic field grabs it, planet lights up. Somewhere 20 light years from here, that same chain might already be running. And there's a specific place they decided to go check. The object at the center of this research goes by the name SIMP 036 plus 933. And it is, honestly, a strange thing to build a study around. It sits roughly 20 light years from Earth. Its mass is about 12.7 Jupiters. Massive, but not massive enough to cross into stardom. And it completes a full rotation on its axis in just 2.4 hours. Jupiter itself, already the fastest spinning planet in our own solar system, takes nearly 10 hours to turn once. This thing spins roughly 4 times faster than the fastest planet we know. When it was first spotted back in 2006, astronomers thought they'd found a brown dwarf, a failed star, massive enough to almost ignite nuclear fusion, but not quite. Follow-up observations told a different story. Only 12.7 Jupiter masses. It was too small to have ever been a failed star at all. It got reclassified as a free-floating planetary mass object, a world sitting right at the blurry boundary between very large planet and very small star, untethered from any host star of its own. Calling it a rogue planet is still fair, even if the technical label is more specific. That distinction is the whole reason it made the shortlist. A world this young, this fast spinning with known aurorae of its own, is exactly the kind of environment where tidal heating would be brutal on any moon unlucky enough to be orbiting it, which made it the perfect place to go looking for an Io of its own, if one exists at all. Here's where this stops being about pretty aurorae and starts being a genuine piece of detective work. The team pulled archival data JWST collected during a transit, the moment something passes in front of the object being observed, dimming its light in a way that can be measured and tracked. Plotted over time, that dimming produces a light curve. Transit data like this is normally how astronomers find planets crossing in front of distant stars. Here, the team pointed the same tool at the aurora itself, hoping to catch a signature buried inside it. Follow the logic. If SIMP 0136 plus 0933 has a volcanically active moon feeding its magnetic field the way Io feeds Jupiter's, that moon's own transit should leave a fingerprint hidden somewhere inside the aurora's light curve. Not a picture of the moon, not even a hint of a picture. Just a statistical dip, a pattern in the noise, evidence that something small and periodic is out there doing exactly what Io does. So, did they find it? When the team ran the numbers on the existing data, the results weren't a triumphant discovery. They were something more interesting, a proof of concept with real, specific odds attached. Applied to this exact system, the method showed roughly a 66% success rate for detecting an Io-sized exomoon, and climbing to about 93% for something the size of Jupiter's moon Ganymede. Sit with that for a second. Those aren't hopeful numbers pulled from a press release headline. Those are calculated detection odds, run against real telescope data for a moon nobody has ever seen and no instrument on Earth can currently see directly. But, and this is the part that keeps this from being a headline about a confirmed discovery, the archival data itself wasn't long enough. The researchers said so plainly in their own conclusions, the existing observation window couldn't place meaningful constraints on whether a transiting moon is actually there. And what they proved is that the technique works. What they did not do, and never claimed to do, is find an Exo-Io. That distinction is the entire reason they're publishing now instead of waiting. Which raises an obvious question. If the method works, why hasn't anyone just gone and finished the job? Before answering that, it's worth understanding why JWST is even capable of this in the first place. Because it's not a coincidence and it's not marketing. James Webb was built primarily to see infrared light, the wavelength range where cool, faint, distant objects reveal themselves. Free-floating, planetary mass objects like SIMP 0136 plus 0933 are dim. They're not lit up by a nearby star, the way a normal exoplanet is, so whatever light they give off comes mostly from their own leftover heat, radiating away at infrared wavelengths. A visible light telescope would barely register something like this. That same infrared sensitivity is also what let JWST characterize the aurora, cleanly enough for researchers to go hunting for a dip buried inside it. No clean aurora data, no light curve precise enough to search. The method only works because the instrument underneath it is good enough to support this level of scrutiny. Here's what most casual coverage of exoplanet science quietly skips past. We have never definitively confirmed a single exomoon, not one, anywhere. There are candidates. A handful of intriguing signals around worlds like WASP 49b, Kepler 1625b, Kepler 1708b, and HD 26893b have all at some point been floated as possible exomoon detections. None has crossed the line into confirmed. The reason is almost embarrassingly simple. Exomoons are tiny, planets are comparatively enormous, and both are sitting in front of a star so bright it drowns out almost everything nearby. Spotting a moon under those conditions has been compared to noticing a single dust speck drift in front of a spotlight from across a football field. And this is exactly why the Aurora Method matters, even without a confirmed result yet. It doesn't require resolving the moon at all. It sidesteps the dust speck problem entirely by looking for the moon's fingerprint instead of the moon itself, the way you'd know someone walked through a room from the footprints in the carpet without ever seeing the person. But footprints can be misread. Objects like SIMP 0136 plus 0933 have their own natural variability. Atmospheric weather patterns, brightening and dimming as surface features rotate into view, instrument noise, cosmic ray artifacts, any of which can produce a dip that statistically resembles what a transiting moon would leave. Every prior exomoon candidate has run into this exact wall, a provocative signal picked apart for years by researchers arguing over whether it's real or noise wearing a costume. None has definitively won that argument either way, which is exactly why this new paper frames its 66 and 93% figures as detection capability, not a detection result. What the telescope could see under the right conditions, not what it has already seen. None of that is the researchers hedging. It's the responsible way to publish a method before you've had the chance to run it properly. Worth remembering next time a headline compresses, "We built a tool that might find this," into "Scientists may have found this." So what would it actually take to close that gap? Turns out closing it isn't complicated, it's just expensive in the one currency that matters most to a space telescope: time. According to their own conclusions, meaningfully testing whether Io-like moons are common around fast-spinning super-Jupiters like this one would require something the archival data simply doesn't have. Roughly a day and a half of continuous JWST observation, applied not just to SIMP 0036 plus 0933, but across somewhere between 4 and 12 known aurorally active super-Jupiters. Not one target, a small survey. Nobody films a hashtag moment out of a telescope scheduling committee. Nobody puts "we requested more observation time" on a highlight reel. But that unglamorous ask is the actual next chapter of this story, and it has to compete against every other proposal astronomers around the world are submitting for the same instrument on the same finite schedule. JWST's queue is famously oversubscribed, far more requested hours each cycle than the telescope can physically deliver. A day and a half sounds small next to a mission meant to run for years. It is not small next to a review committee weighing hundreds of equally strong proposals for what gets the telescope's attention next. Which brings up the real question worth sitting with here. If this method works at scale, it hands astronomers something they've never had: a working technique for hunting exomoons that doesn't depend on resolving a point of light too small and too dim to ever separate from its planet. Every previous exomoon candidate has come from straining at the very edge of what direct observation can do. This approach comes from somewhere else entirely, from what a moon does to its environment, not what it looks like. And underneath that sits a bigger question. Io's relentless volcanism exists because of tidal heating, the same mechanism suspected of keeping liquid water churning under the icy shells of Europa and Enceladus, two of the most closely watched targets in the entire search for life beyond Earth. If tidally heated, volcanically active moons turn out to be common around massive planets elsewhere in the galaxy, the list of places worth searching gets longer and stranger than most people currently assume. Not just for volcanoes, for everything tidal heating might be quietly powering underneath them. Every world we've ever called potentially habitable has had to earn that label the hard way through direct imaging and years of follow-up. A working exomoon survey method adds a new category entirely. Not find a second Earth around a sun-like star, but find a second Europa around almost any large enough planet, anywhere. Tidal heating doesn't need a nearby star at all. Free-floating worlds like this one don't even have one. So here's everything in one breath. Jupiter's moon. Io is the most volcanically active body in the solar system because of tidal heating, and its volcanic gases feed Jupiter's own auroras by riding along its magnetic field lines. Researchers took that exact relationship and asked whether the same signature could be found somewhere else, specifically in JWST transit data on SIMP 0036 plus 0933, a fast-spinning 212.7 Jupiter mass world 20 light-years away. Running that data through a new detection method produced strong theoretical odds, roughly 66% for catching an Io-sized moon, 93% for something Ganymede-sized. But the existing data was too short to confirm anything. No exomoon has been found, only that the method works. Getting a real answer needs about a day and a half of dedicated JWST time across several similar systems, time that hasn't been granted yet. None of that is a confirmed discovery. All of it is a genuinely new door left open in a search that, until now, has produced 0 confirmed results in the entire history of exomoon hunting. Whether anything walks through that door is still an open question, and that's worth sitting with rather than rushing past. If you want to be here when that survey data actually comes in, when someone finally points JWST at a handful of these worlds, and we get a real answer instead of a probability, subscribe and turn on notifications, because I'll be covering it the moment it's published. Here's the question I'll leave you with. If you were in charge of allocating James Webb's observation time, would you spend a day and a half of it chasing a 66% shot at finding the first confirmed exomoon in history, or keep that time on targets with a more certain scientific payoff? Tell me which one you'd choose, and why. I read every single one.